Yeah, the next one is covering basically our contributions to activity E5, which as Sune mentioned before, is looking into performance modeling and temperature behavior of BIPV. I'm going to cover a few extra subjects as well in this talk. And the basic framing title for this is the performance of this BIPV curtain wall system that you saw in the technical tour earlier today, if you're here on site. If you're not, here's a short overview of the system. So you can see the picture to the top right. We have this office container, which was retrofitted with facades, BIPV facades, curtain wall elements. On the south side, shown here to the right, we have some modules that are internally mounted, some that are externally mounted. So we have different air spacing behind the modules that introduces different ventilation. And on the west side that we can see here facing us directly, we have 5 differently colored modules based on colored interlayers within our glass modules. And then on the system, we're performing extensive monitoring. So we're monitoring module temperature, we're monitoring the individual module performance, since each module is outfitted with a power optimizer. We're monitoring DC data from the inverters, and on our weather station, we're also monitoring irradiance and weather data, which allows us to model this system and compare the modeling results with the actual monitored performance results. And we then brought this system into IEA PVPS task 15, specifically activity E5, where there is an intercomparison going on between 5 different projects that all are different implementations of different BIPV solutions in different locations, different climates, and so on. And there's 2 main focus areas, the operating temperatures and the performance modeling. I'll start with the first one, and this is work done by some of our Canadian colleagues who looked into applying the IEC TS 63126 technical specification. And this basically tells you that if you have an integrated PV system or you have a system in a very hot environment, you have to do extensive additional testing. So it tells you that in addition to what the normal IEC 61215 prescribes, you have to do tests at elevated temperatures. But we knew from our experience that actually not all our systems are getting operating values above 70 degrees Celsius. And we wanted to look into, well, how does that compare? Do all these systems stay below these 70 degrees? Can we maybe influence some change in the standard so that this extensive testing is not necessary for all systems? So that was the first question. Do we actually reach these 70 degrees in most systems? And the second question was, can we maybe approximate that and from the installation location and the system configuration, decide whether this extended testing is needed? And you can see here, quite small, 2 world maps that show where this testing would be necessary depending on different installation options. So the orange areas is everywhere where this testing would be necessary if this King's model is applicable, depending on either ventilated or non-ventilated setups. So what we found when we tried to model the operating temperature using this King's model, which is shown here in the box to the right, it's basically a very simple model that only uses the irradiance, the wind speed, and the mounting configuration to calculate the cell temperature of your modules. Then we were able to show that, yes, this model can be accurate, but it is not trivial to use. So this model provides a table of common values depending on mounting configuration and module type. So for a glass module that is mounted directly on insulation, you have different coefficients than for a glass backsheet module that is mounted on a tracker. That makes sense. You have a lot of different ventilation. You have different amounts of heat transferred away from your module. So of course you have to investigate different parameters. But we were able to show that actually these parameters that would make logical sense. So if you have a glass module, then actually not the glass coefficients are the ones that fit the data best, but it's one of the coefficients in this data set. So it's it's very difficult to actually apply this model to filter for installation location if the logical parameters don't make sense in the end. And then the second question, as I mentioned before, is do we actually reach temperatures above 70 degrees Celsius? And again, there is a yes, but there was actually only a single system out of the 5 systems that we looked at that actually reached above 70 degrees. And it actually was the system here at DTU, but only the part that was installed with an insulated backway. All the other systems, even though they are mounted partially very close to insulation, are not truly insulated systems, you could say, because they do not actually reach these high operating temperatures. And that means that the statement that we have in our technical specification, which says whenever you have an integrated system, you have high operating temperatures and therefore need to do extensive high temperature testing, is maybe not that valid. So our colleagues in task 15 are going now to the standardization bodies and are discussing whether we can affect the new versions of these standards to make it a bit easier for BIPV manufacturers to allow for less testing needed. And now I want to touch on some other subjects that we discovered during the monitoring of our system. One of the things we noticed when we looked at all this temperature analysis is that due to the glass modules we're using, we have a very high thermal capacitance. So what I'm showing here is the operating temperature of the modules on the colored west facade. And you can see here that the peak in module temperature is about 45 minutes or half an hour to an hour delayed from our peak in irradiance. And that is basically due to this heating cooling behavior with the high mass of our modules, where basically the irradiance absorbed in the cells has to heat up both two panes of glass, and that just takes some time. We were also able to show that the ventilation has a very large impact on the performance of our modules. And we could show that if you ventilate the backside of your modules, you get operating temperatures that are about 40 to 50% lower than for the fully insulated modules. We also looked into how do typical, or are still looking into how are typical PV modeling tools modeling BIPV and specifically our system, where we looked into the system advisor model by NREL, which is very commonly used in PV modeling. And we modeled and measured the temperature, modeled and measured DC power, and in some cases, so not for our case, but for some of the other studies, they also looked at AC temperature. And we saw in our case specifically that we have relatively high modeling errors in winter when we have very low irradiance. And that is basically due to a relatively high correlation between the irradiance modeling error in SAM and the DC error that we actually observe from the SAM output. And again, this will be presented in a report early in 2024. And then we looked also into further aspects in our system. So as I mentioned just briefly before, all of our modules are outfitted with power optimizers. And it was mentioned in task 12, in the task 12 presentation, no, task 13, sorry, from Jan earlier, that module level power optimizers are interesting to look into. And we saw some also very interesting results in that our optimizers barely ever reach the efficiency that is stated in the module data sheets. There is some aspects that could be relevant here, but if you look at the bigger plot here, you can see that our inverter is operating almost normally. So that is a typical inverter operating curve. Whereas for the optimizer efficiency, you can see that there's a lot of green and blue points all over this graph, showing us that we have inverter efficiencies that are below 94 or around 94%, whereas the datasheet value says that the weighted efficiencies should be somewhere around 99%. So there is certainly something going on here, which we will be investigating in the future as well. Our oversized inverters and optimizers might play a role, but we're not sure that this is a major role. We currently believe that that is only a minor role. and that is mostly related to this conversion ratio dependence. So that means if you have a lot of modules in your facade that operate slightly differently, either due to mismatch from the factory or shading or different mounting configuration, that introduces these additional losses in the optimizers. But again, that will be published in a later paper. And then we also looked at the performance of our colored modules, where we identified a few issues when modeling this. First one of them is that these colored layers absorb light naturally, and this light contributes to parasitic heating in our module. And we were able to show that this is directly correlated with the reflection losses on our samples. So that means the more this colored layer reflects and doesn't absorb, the cooler our module stays and the higher our efficiency is. Whereas if these colored layers absorb a lot of light, they lead to a lot of parasitic heating, and that also reduces the efficiency. We're also able to show that the angular dependent transmission losses, or basically the angular effects of these modules, are a lot stronger than on uncolored modules. And that means that if you have very diffuse light, like today, you will see several percent higher losses than you would on a normal installation, just due to light coming from different higher incidence angles. And finally, we were able to show that spectral mismatch is a significant factor for these colored modules. So for example, in this case, the red module, due to the amount of light that is transmitted, or the part of the visible spectrum that is transmitted to the cells, it actually performs much better in the early morning and late afternoon compared to how it would operate at noon, simply due to the spectrum mismatch. And that brings me to the conclusions here already. So we investigated this container, this BIPV facade test site, and brought in task 15 subtask E5. And there's an IEA PVPS report currently in preparation, which is expected to be published in early 2024. And for our own results, we're currently working on a journal article, which will also include the raw data from our system, so that modelers can use them to verify their own models. And yeah, just a short reminder from what Sune said before, phase 3 will also include a lot of modeling on performance, degradation, and glare, and also looking at color PV.